Okay, this is section 1.4, part 2. Okay, example 4. Discuss the continuity of the function f of x equals the square root of 1 minus x squared. Okay, the first thing we might want to do is find out what the domain of this one is, because whenever you have a square root, you can't take the square root of a negative. So to do the domain statement, 1 minus x squared, the radicand is what that's called, must be greater than or equal to 0. And I want to solve that inequality. So if I factor the inequality, left side, I'll get 1 plus x times 1 minus x. And if you recall from pre-calculus, what we're going to do is we're going to find out where it actually equals 0, because that's the only way you can change from positive to negative is to go through 0. So I'm going to solve where it's equal to 0, and that's when x is negative 1 and when x is positive 1. And then we're going to do something here called a number line analysis, which you may or may not have seen in pre-calculus. I teach my pre-calculus classes this for sure, because it's a wonderful tool. And it's a tool that we're going to use in calculus pretty extensively. So make sure you pay attention to this tool and how it's developed and how we use it, because we're going to use this a lot. Okay, so on the number line, I'm going to put from left to right, small to large, all of the numbers that I found where it equals 0. Later on, we'll also be worried about when there is no value for certain x's, like if you had something like 1 divided by x minus 2, we'd want to include 2 in this as well because the function doesn't exist there, but that's not an issue now, so I'll reintroduce that later. So since we got this from equals 0, we're going to put a solid dot on both negative 1 and 1 on the number line. If there were a 2 where it didn't exist, I'd put an open circle to help me remember that that's a place where it doesn't exist. Okay, so this is the f of x number line. So we want to label which number line we're talking about, because there are going to be at least 2 more of these for different things. So it's really important you tell me which function that is. And then that number line has, by those 2 dots being plotted, has separated the number line into 3 chunks. The parts, the numbers below negative 1, the numbers between negative 1 and 1, and the numbers bigger than 1. And so what I want to do is I want to test 1 minus x squared at different places. So I'm going to pick first a number to the left of negative 1. And it doesn't matter which number you pick to the left of negative 1, because whatever one of those does, the others do the exact same thing. That's why they're in 3 chunks here, because whatever number you pick is representative of all other numbers in that part of the domain. So if I pick, for example, negative 2, then 1 minus x squared which is 1 minus 4, is negative 3. And I'm sort of interested in what the answer is, but not so much as what I'm interested in is that a positive or a negative answer? That's a negative answer, and what that means is that all numbers that I could have chosen to the left of negative 1, every single one of them would give me a negative result. Okay, now let's pick something between negative 1 and 1, like 0. I always pick the easy numbers because I'm chicken, I guess. So 1 minus 0 squared is 1, and that's important to know, but more importantly, that's a positive number, and that means that any number I had picked between negative 1 and 1 would have given me a positive result. Okay, now to the right of 1, we can pick any number we want, so how about 3? Notice I'm picking things that I like to work with, not anything hard. and that gives me -8. And again, the result is that it's negative, and that's the important part for me. So the question that we were trying to answer with this number line analysis was, when will 1 minus x squared be greater than or equal to 0? Well, the answer is right there in your number line analysis. It's 0 at -1, and greater than 0 between -1 and 1, and then 0 again at 1. So those are the places where 1 minus x squared is greater than, between -1 and 1, or equal to, at -1 and 1, 0. Okay, so that means, therefore, that the domain of this function is every place, every x value that would give us a number greater than or equal to 0, which will be from -1 included to 1 included. Had this been strictly greater than 0, we would not have included the endpoints, and it would have been open parenthesis -1 to open 1 parenthesis after the 1. Okay, so now if you look at Theorem 1.4, I sort of used this already, but I might as well say this is where it is. The limit of the nth root of x as x approaches c is going to be the nth root of c, as long as it gives you a real number. And we said something like this before. If n is even, c has to be greater than 0. But if n is odd, c can be can be anything. Okay, so for that reason, as long as we're taking the square root of a positive thing, which is its domain, this function is continuous on the open interval for sure. When it's positive, -1 to 1. Then we have to test the endpoints of that interval. And I could easily say that the limit as x approaches -1 from the right of f of x, and this can be done by substitution as long as it doesn't give us an invalid number. This will be 1 minus -1 squared, which is 0, and that's the same thing as f of -1. So it's continuous at -1 from the right. Then we can look at the 1, the other endpoint, from the left side. Since it's a radical function, we can do that limit by substitution, provided it doesn't give us an invalid answer. It gives us an answer of 0, which happens to be the value of f of 1. So that means it's continuous at x equals 1 from the left. So our grand final conclusion is, if it's continuous on the open interval from -1 to 1, and now we know that it's continuous at both endpoints, we can claim that we have continuity on the closed interval -1 to 1. So again, radical functions, we can now say, will be continuous on their domains. Okay? Take that as a given. Now, another thing that we could have used here is Theorem 1.5, the composition of functions. To explain this a little bit more, the limit that we did, I kind of slid through and just said we can do it because it's a radical function, but this Theorem 1.5 actually says why that's so. This limit, because this is the square root of a quadratic function, we can use the composition, the limit of the composition function property, and take that limit inside. of the polynomial function, and we know that the polynomial function itself can be evaluated using substitution. So that would be 1 minus negative 1 squared, which, that's now the same. So the only thing I add here is that that substitution I did is valid. This step right here, because of Theorem 1.5, makes the substitution under that radical viable and doable. So that's what we were using. Okay. So there are some properties of continuity. Theorem 1.11. If b is a real number and f and g are continuous at x equals c, then all of the following functions are also continuous at c. A scalar multiple, a number times a function. If f is continuous at c, 5 times that function will still be continuous at c. Number 2, sum or difference of two continuous functions at c will be still continuous at c if each one individually is continuous at c. And then the product of two functions will be continuous at c if f and g each are separately continuous at c. And for the quotient of two continuous functions at c will be continuous at c, except, and this happens every time we have a quotient, except for when you're trying to divide by 0. That one we have to disallow. Okay, then in the next slide, the list below summarizes the functions we've studied so far that are continuous at every point in their domains. That includes polynomial functions, rational functions, radical functions, and trigonometric functions. So if you combine 1.11, which allows you to multiply any of those by a scalar, like times b, or add or subtract 2 of those, or multiply 2 of those, or divide 2 of those, as long as you're not dividing by 0, that opens up a whole bunch of functions that are going to be continuous in their domains, at all points in their domains. So that means that if you look at example 6, all of those functions listed will be continuous at every point in its domain. The sum of a polynomial x plus a trigonometric sine of x, the scalar multiple of tangent of x, 3 times tangent of x, and the quotient of x squared plus 1 over cosine x. That's the interesting one because, of course, when you divide, that sort of takes some things out of the mix. So we're going to say this is continuous on the domain of all of the polynomial function, which is all reals, and the domain of the trig function, which is all reals. But because of the, so this would be continuous for all reals if we were adding, subtracting, multiplying those two. But because of division, it will not be continuous at any point where cosine of x equals 0. And if we recall, that is true for odd multiples of pi over 2. This is one way to write odd multiples of pi over 2. Another way to write odd multiples of pi over 2 is to say 2n makes any integer even. Makes any integer times 2 is even. If you add 1 to an even number, it's odd. And that number, odd number times pi over 2, is a way of saying odd multiples of pi over 2. And the expression on the left is really the same thing if you just distribute the pi over 2. They're the same. Okay, so this one, f of x, would be continuous for all real numbers that are not of the form, so they're not equal to I'll use the second expression, the one right above it. Odd multiples of pi over 2. So it's continuous as long as it's not an odd multiple of pi over 2. The function will be continuous everywhere else. Okay. So this next theorem, which we've kind of touched on already, says that if you have a composite function, we can talk about the continuity of a composite function by the theorem 1.12, which says if g is continuous at c, that's the inside function, and f is continuous at g of c, that is, if you put c into the g function and then take that answer, and that answer is continuous for f, then the composite function given by f of g of x will be continuous at c. Okay, so let's do example 7. F of x equals tangent of x. So to find continuity, we need to know its domain, because f of x, being a trigonometric function, will be continuous everywhere on its domain. So to think of that, I need to realize that tangent of x, according to the quotient identities, is equal to sine of x over cosine of x. And that implies that cosine of x can't be 0, which from the earlier discussion means that x can't be an odd multiple of pi over 2. And so that means that f is continuous everywhere except at odd multiples of pi over 2. So it's continuous for all reals such that x is not equal to an odd multiple of pi over 2. Okay, which implies f is continuous everywhere except those places. Now let's look at example B. By the way, you could look at a graph of tangent x on your calculator and see that those vertical asymptotes are places where the tangent graph is not continuous, and that totally makes sense. Okay, g of x is defined as a piecewise function to be sine of 1 over x, as long as x is not 0, but equal to 0 when x is 0. So let's look at this one. Of course, the domain of sine of 1 over x is x can't be 0, which makes sense, and that's why they defined x to be 0 when x is 0. So let's look at the limit to see if it exists, because they've defined, we now know that g of 0 is 0. So let me write something here. Step 1 for continuity at a point is, does the substitution of 0 in there give you a real number? The answer is yes, it does. Second, does the limit as x approaches 0 exist? And for that to be an existing thing, that means that the limit from the left side and the right side have to be the same thing. So we're going to explore both of these one-sided limits. Okay, as long as x is approaching 0, notice I didn't say where x is 0, but as it's approaching 0, the correct expression for g of x in both cases is the sine of 1 over x. Okay. So if we take a number really close to 0, I'll just make up some positive answers because those are easier to think of, like 0.1. What's 1 divided by 0.1? Well, it's 10, sine of 10. Okay. Now let's get closer to 0. Let's say 0.01. 1 divided by 0.01 is 100, so that would be sine of 100. So the argument is getting bigger. So sine of 10, sine of 100, sine of 1,000, sine of 1,000,000. Is the sine graph approaching a particular single value as x gets bigger and bigger? Well, no, you know that the sinusoid continues to do this forever. It doesn't approach a single value. So this limit does not exist from either side, actually, because we would be taking the sine of negative infinity for the negative x's. And so because that doesn't exist, that's a failure of our test for continuity at 0. And if we have a failure, that means it's not continuous at 0. But otherwise, since sine of 1 over x, because 1 over x is a continuous function, it's a rational function, except for at 0, it's not continuous at 0. And the composition of sine of that, sine would be continuous everywhere for any real number you put in. This implies that g is continuous everywhere. Well, I get my pen to write. There we go. It's continuous for all reals, except for the one that we have shown where it's discontinuous. So it's continuous for all real numbers as long as x is not 0. So I forgot to write this. I said it, I believe, but let me say it. This failure of the second test implies that g is not continuous at x equals 0, which leads us to the conclusion that it's continuous everywhere else because of the type of functions we're dealing with, the composition of two functions that would be continuous on their domains. All right. Then C, h of x is equal to another piecewise function, x times sine of x, 1 over x, for x not equal to 0, and h is equal to 0 when x is 0. Okay, so as we already established a minute ago, sine of 1 over x is continuous for every number except for at 0, because 1 over 0, of course, is undefined. So we can start with that h is continuous everywhere, well, for all real numbers, except perhaps at x equals 0, which we haven't done yet. So let's do the three-part test. Does h of 0 exist? Is it defined? Yes. When x is 0, the answer is supposed to be 0. So we passed the first test. Second test. What's the limit as x approaches 0? And to discover that, we have to approach it from the left side. and from the right side. For the left side and the right side of 0, the appropriate expression for h of x is the one on top, x sine of 1 over x for both. Of the limits. Okay. So for this one, to do this process, I don't know exactly how to do that limit as it is. So I'm going to think about this for a second and see, is there something I could compare to that? Well, this is going to seem like magic, perhaps, but let's let, I can't remember which one. Okay, let's let h of x, I may have the letters reversed from how the theorem is stated, but that's okay, no big deal. Let h of x be the opposite of the absolute value of x. And how did I come up with that? Well, that's not the easiest thing to see. Well, I mean, once you see it, it'll be, oh yeah, that makes sense. Oh, wait, I don't want to use h. I just realized h is the name of my function in this problem, so I don't want to reuse that. Excuse me. So I'm not going to be using, for sure, I'm not going to be using the same letters as the theorem has, but that's all right. It's the idea of the theorem that matters, not the name of the function or functions that you're using. Okay, so let's let this be, I'll go ahead and call it f of x. And let's let g of x, I mean, make sure I haven't used g already in this problem. Nope, I haven't. Be the function that's absolute value of x. Now, if you'll graph f of x in your calculator, and to get the absolute value symbol for y1, which is negative absolute value of x, type the opposite of first, and then go to math, hit the math button, and go over to NUM, the number submenu, and ABS is your first option. Choose that and then type x. And for y sub 2, just do absolute value of x, same way. And you should see, oops, well, pretend like that was nice and vertical and straight for just a second. The absolute value of x, the g function, looks like this. Which, by the way, this is one I would have expected you to be able to graph without your calculator. Just saying. And f of x would be this one. Just the g of x graph reflected over the x-axis. And then I want you to graph the h function, the part that we're worried about, the part where x isn't 0. Graph x sine of 1 over x. And what that's going to look like is something like, looks sort of like this. I don't think I did a great job of drawing this because I think it's symmetrical with respect to the y-axis, and I didn't make it look like that. But anyway, I'm hoping you see that as you get, if you look at this graph, would you believe me if I said this statement, that f of x is always less than or equal to h of x, except for 0 where h isn't defined? Well, actually it is. Oh yeah, that would be true. Which is always less than or equal to g of x. And from the graphs, would you furthermore state that the limit as x approaches 0 for f of x, if you look at it from both sides, it's headed to 0. And for g of x, the same thing is happening. As x approaches 0 from both sides, g of x is headed towards 0. And so, do you remember the name of the theorem I'm trying to reference here? By the what theorem? Some people call it the squeeze theorem. Some people call it the sandwich theorem. And the third name is the one I never use, the pinching theorem, I believe is the name. So by the squeeze theorem, that is what tells us that the limit as x approaches 0 of h of x is 0. Okay, well that was a pretty long argument for part 2. I didn't really know how to do the things I set out to do from the left and right side. So doing the squeeze theorem allowed me to finish that. So the last thing is the limit as x approaches 0 for h of x actually equal to the answer for h of substituting in 0, h of 0? Well, yes, and so consequently, that tells us that h, therefore, is continuous at x equals 0, and everywhere else it's continuous for all reals, as we set up here at the top. It's continuous for all reals except for perhaps at x equals 0, because the rational function 1 over x is continuous. The composition of sine and with 1 over x is continuous. I should have said on its domain. So keep saying that in your head, on its domain, on its domain. And then x, a polynomial function, is continuous for all reals. And the product of two continuous functions, so we're stuck with on its domain as part of that, it's continuous everywhere on its domain, which is all reals except for perhaps 0, because that's not in the domain of sine of 1 over x. But we just proved that it is continuous at 0 because h of 0 is defined to be 0. So therefore, the grand final conclusion is that h is continuous on the interval from negative infinity to infinity. Okay. Now, we're going to talk about something called the intermediate value theorem. Theorem 1.13. If f is continuous, and this is why we had to harp so much on continuity, is because several of our major ideas in calculus depend on having a continuous function. So we have to know that it's continuous before we can apply theorems that require continuity to be true. So if f is continuous on the closed interval from a to b, I'll draw a picture to help you see that, and f of a is not equal to f of b, so I'm just going to draw something random for the graph of f. And let's say a is right here, which means f of a for this graph is there. And let's say b is here. And so f of b here is actually lower than f of a. It could have easily been just the opposite. I could have easily picked an a value that had a lower value than the b would produce. But it just so happens to be that the order is f of b is smaller than f of a, for this picture anyway. But it says if f of a and f of b are not the same thing, and k is any number between them. They're being specific about not saying f of b is smaller than f of a because it could be reversed. So if I picked any number, let's just say this one, y equals k, then that number has to be between f of a and f of b. Then there's at least one number on the interval from a to b, and that number is called c, such that, and there it is right there, f of c equals k. So somewhere between a and b, the existence of a number c that will produce k as a result of substituting c into the function, that c value has to exist somewhere between a and b to produce any value between f of a and f of b, not just the one I picked, but anything between them is fair game. Now notice, like right here, there's some values that are not between f of a and f of b. That's fine. That's not what we're worried about. If I pick a number between f of a and f of b, then there's going to be at least one value of x that will produce that y value that's between f of a and f of b. Okay, this is the intermediate value theorem. And it implies that you have to have continuity, because if I had a graph that was not continuous, let's say this one, and here, well, I did it again. Oh well, sorry about that. If I pick A to be, say, here, and f of a is here, and I pick B to be right there, which means f of b is about right there, am I guaranteed that there's a c value between a and b such that I'll get an answer for y that is, say, right there? Is there any place between here and here where the graph has that y value? Nope. It nowhere happens. So that guarantee that there will be a value of c that produces that y value is not necessarily going to be true on a discontinuous function. But if it's continuous, the existence of the number x equals c is guaranteed. And for that reason, this, amongst other theorems, is called an existence theorem, because the existence of the number c is assured that will produce the y value, k, that's between f of a and f of b. And so, again, this is called an existence theorem. And that number is an intermediate value. It's between f of a and f of b, hence the name intermediate value theorem. And if you're accessing this theorem and you want to refer to it in short, you can call it IVT, capital letters I and V and T, is a recognized abbreviation for the intermediate value theorem. Okay, so the proof of this theorem, which we're not going to go into, is based on a property of real numbers called completeness. The real numbers completely fill up the real number line. There are no points on the real number line that are numbers that aren't real. It's completely filled up with real numbers, and there's no gaps or holes in between them. So the intermediate value theorem states that for a continuous function f, if x takes on all values between a and b, then f of x has to take on all values between f of a and f of b. Here's an example to help you understand what we're talking about. You can probably understand if I talk about a person's height over time, because you don't all of a sudden go from 3 feet tall to 3 foot 5 inches or something. You don't skip to that. You have to grow through every height in between. So let's say there's a girl who at the age of 13 is 5 feet tall, and on her 14th birthday she's 5'2". 5'2". Isn't it necessary that for any height between 5 feet and 5'2", that sometime between her 13th and 14th birthday, she was, for example, 5'1" or 5 foot half an inch, 5 foot 3/4 of an inch, anything between 5 feet and 5'2", if you pick that number, she had to be that height at some point in time between her 13th and 14th birthday. Okay, so that means that she has to have been 5'1", for example, at some point in that 13th birthday to 14th birthday year. Okay, now it is possible. The picture I drew didn't have this possibility, but let me make one that will. So here's F, and let's say A is right here, and so F of A is there. And let's say B is right there. So F of B, oh, and F of B this time is larger, which is good. I wanted to have you see that at least once. And if I were to randomly pick a value of K, like this number right here, starting at A, so starting right here, does this function ever take on, and by the way, I meant for F to be continuous, does it ever take on the value of y equals K? Well, it does right there. And then it happens again right there. So I'll call this one C sub 1 and this one C sub 2. And again right there, call that one C sub 3. And then we get to B and stop looking. So is it possible that you'll have multiple values of C between A and B for which that chosen value of K that's between F of A and F of B, that you'll have, like in this case, 3 places that make that happen? Yes, of course. The existence theorem only guarantees that you have at least one. That doesn't mean that you can't have more than one place where that happens. So that's an interesting result. But the existence of one, at least, is what the theorem gives us. Okay, so let's see what's next. Now, one of the major uses of the intermediate value theorem is one that you've actually already perhaps encountered, is that if you have a function that you can show is, well, let's say it's a polynomial, so we know it's continuous, just so that you have that basis. So it's continuous. Let's just say that's a given. And I picked on polynomials because you've done this with polynomials probably the most in your life. Let's say that at x equals a and x equals b, you have a y value for one of those. It doesn't matter which one. I'll make a. One of those values has a negative output. So f of a is negative. And then B has an output that's positive. Okay, so all of this is given to you. What could you conclude has to happen somewhere between A and B at least once? Well, if you think about it, the graph has to pass through the x-axis at least once. I want to make this so it's exactly once, but at least once. So there's at least one time that that happens. Well, so when you've solved equations like, I don't know, x squared minus 4 equals 0, which you probably know fast ways to do that. But if we were trying to solve that, if I were to pick a number like, negative 3, negative 3 squared is 9, 9 minus 4 is 5. So that's a positive answer. And if I were to pick a number like, I don't know, 0, 0 squared minus 4 is negative 4. Oh, sorry, I wrote 5 and I think I even said 0, but I didn't write it. I said the answer. Oops. That's not what I wanted to say. F of negative 3 was 5. That was the calculated value. what I want to point out is that it's more specifically a positive answer. And f of 0, 0 squared minus 4 is negative 4, is definitely less than 0. Can't we claim, therefore, that somewhere between x equals negative 3 and x equals 0, f has a 0. Remember, a 0 of a function is a place where the function has a y value of 0. It's also sometimes called a root. Sometimes it's called an x-intercept. Those are various names. But wouldn't you be able to claim for sure that that has to be the case? It's somewhere between negative 3 and 0 for the function I gave you, which is not what's pictured over there to the left, but somewhere that has to happen. And then, of course, you know that that's really at negative 2 is the one that makes that true. And by the way, x equals 2 is the other 0 of that function. But this is the one, x equals negative 2, that we're guaranteed will happen somewhere between negative 3 and 0. Happens to be known to be negative 2. So that's kind of a intermediate value theorem that's very useful thing, is that if a continuous function has a negative and a positive output for various x's, then between the x that gives you a negative output and the x that gives you a positive output, somewhere between those two numbers for x, there'll be a number called c that will produce f of c being 0. Has to happen. Okay, so let's use that in example 8. We're supposed to use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 in the interval from 0 to 1. Now, in the last example, I chose a polynomial function that you could easily factor to be x plus 2x minus 2 and solve and get x equals negative 2 and 2. So that one I picked on purpose so you could easily, readily understand it. Do you know how to factor this polynomial to solve for where it's equal to 0? I'm going to say you don't. Let's just pretend like you don't have a clue how to factor it. So we'll say that the intermediate value theorem requires that we know what kind of answer we're getting at the endpoints 0 and 1. So if we substitute 0 in, we get negative 1, which of course is negative. And we put in 1. 1 plus 2 is 3, plus 1 is 2, and that's positive. So by the intermediate value theorem, oh, and I have to have said f is a polynomial function. So it is continuous for all reals. And because we have that continuity, the intermediate value theorem applies. So I'll come back to this. This should have actually been one of the first things I said. By the intermediate value theorem, then, C must exist such that C is between 0 and 1, such that f of C equals 0. Because we have one result that's negative and the other one's positive, so we have to pass through y equals 0 at least once. Okay, so We have at least one 0. We don't know, there might be more, but we know that there's at least one. And if you graph this function and look at it between 0 and 1, you'll see that it actually crosses through at some unknown place. We may not be able to find that number without technology. It could be that we could factor this and find out what that is exactly, but maybe not. I'm going to make mention of something called the bisection method for approximating the real zeros. Basically what this says is that, and I'm going to use the example we had above because it's going to be easy. So let me change back to a pink color so that you know we're still working with that one. Okay, so if I know that there's a 0 between -3 and 0 somewhere, what I can do is I can split that into half. I wish I'd picked -4 instead. Oh well, I didn't. It would have been so much easier. Anyway, so if I were to take from -3 to halfway between -3 and 0, and to be halfway between is the average of those two values. And the average is -3 plus 0 divided by 2 is -3 halves. Or somewhere between -3 halves, same point we just calculated, and 0. That place that creates a 0 value, which we know is -2, is in one of those two intervals. So if we found f of -3 was positive again, I'll just say that that's true, and f of -3 halves, let's see, what would that be? It was x squared minus 4, right? Yeah. So x squared would be 9/4 minus 16/4 is a negative number. So that would say that there is a 0 in this smaller interval. Maybe there's another one over there between -3 halves and 0. We know that that's not the case, but we know that we can narrow it down. So now go take that as a given interval where one answer is positive, the other one's negative, and bisect it. So go to -3, from -3 to the average of -3 and 3 halves. To recall that the average is the sum -3 plus -3 halves divided by 2, which is -9/4. And then go from -9/4 to -3 halves. So we're taking this interval and splitting it in half, like we did the interval from -3 to 0 to begin with. And then we decide, is it in this interval between -3 and -9/4, or between -9/4 and -3 halves? And so you calculate f of -3 being positive, -9/4 is also positive, and so it's not in that interval. And f of -3 halves is negative. And if f of -9/4 is positive, then that would put us somewhere between these two. And then we could split and split. So this is called the bisection method, where you keep splitting the interval and testing the first and last number to see if there's a sign change. And if there is, there's a 0 in that interval. If there's not a sign change, then there's not a 0 in that interval, and you discard that and then bisect the smaller interval. And you could do this forever. Of course, it's kind of a pain in the rear to keep going like this, but this is a technique that especially computers could do this kind of repetitious thinking process and just keep applying the same logic to it. It could very quickly, with a computer program, figure out a 0 for that function. And so we'd be able to close in on that 0 by continually bisecting these intervals and testing to see if a 0 is on the newly created half of the original interval. All right, so anyway, that ends this lesson. I will see you in class.